I'm not going to repeat everything that I just said, but I will just summarize it briefly for the benefit of the Zoom recording. Your test is next Wednesday. It's going to cover the sections from chapter 1 and chapter 2. Today we're going to do 2.5 and start 2.6. This Friday, your next quiz will open. Monday, we'll finish 2.6 review for the test, and the next Wednesday is your test. All right, if nobody has any further questions or comments, then we are going to continue. All right, last time we started 2.5, which was called, had a pretty long name, 2 quantitative variables. Can't spell. I wish these text boxes would default to a bigger width. 2 quantitative variables, scatter plot and correlation. Really, all we talked about last time was what a scatter plot was. Basically, it's just a bunch of dots on a graph. I had shown you some pictures of some. I do have the second edition version of the textbook open as a PDF. I'm going to pause the recording just for a second. Okay, so I wanted to show, remind you what some scatter plots look like. I do have a PDF of the book pulled up. We're going to share it here in just a second. And I have no idea what page these are on. Looks like they will be in the low 100s. So we'll say 130 and see where that takes us. That takes us right about there. Wow. Good guess on my behalf. Let me blow this up so that one of these is the prime focus. There we go. Throw that up to the top of the screen. When you see a scatter plot, your horizontal axis should be labeled measuring something. This is measuring something's acidity in pH. And then the other axis, the vertical one, should also be measuring something. This is measuring average mercury. I didn't go over the content of the scatter plot, but it's measuring the acidity of the lake versus the average mercury content. And then each point represents a data point gathered from one case. For example, we'll say this one right here, if I were to drop straight down, somebody went to a lake and measured a pH of about, we'll say 3.7-ish, and an average mercury of level in the fish that they caught of almost 0.9. But each one of those represents a single case's pair of measurements. In this case, it was measuring acidity in a lake versus average mercury level in fish. I know it doesn't say all that here, but I've done this example many times. I just remember the context. All right, let's go back to the whiteboard. All right, so we talked about that, and we also talked about the concept of correlation. What all did we say, if anything, about correlation last time? Did we say anything? Oh, correlation doesn't imply causation. All right, we did say that. I'm going to go ahead and type that because it's important. Correlation does not imply causation. It's a very common argumentative technique, which always fails. I mean, there might be some causation in there, but just because two things are correlated doesn't mean that one of them is causing the other. We've talked about some examples like that. When the number of ice cream sales go up, so do the number of drownings. It's not like one is causing the other, but there's a confounding variable, usually the temperature outside. The higher the temperature, the more ice cream sales. The higher the temperature, the more people swim, and therefore the more drownings there are. But being correlated does not mean that one thing is causing the other. A lot of people just incorrectly assume that. You shouldn't do that. But when I was asking if we talked about correlation, what I was really asking is, did I define what correlation was? Okay, then why don't we start with that? Correlation is a measure of the strength. I mistyped something. A measure of the strength and direction of a linear association between two quantitative variables. Direction usually starts with a D. A measure of the strength and direction of a linear association between two quantitative variables. Let me translate that into a little bit more English. In other words, a number that answers two questions. Number one, let me move this text box up just a little. Number one, on a scatter plot, is there an upward trend, upward or downward trend? Because remember, when we have a scatter plot, we have a bunch of dots on a graph, and they may be scattered all over the place, but collectively they may be moving kind of upwards as you move from left to right, or they may be moving downward from left to right. So correlation is a measure, which is just a number, that will answer the question, is in general the data going up from left to right or down from left to right? And the second question that this correlation measure answers is, how, quote, linear is this trend? So we'll have one number that answers both of those questions. As far as the first question, it's really easy to figure out what the number has to be to indicate an upward trend versus a downward trend if you know anything about slope from an algebra class. Does anybody remember anything about slope from algebra 1, algebra 2, college algebra? Y equals mx plus b, rise over run, and there's a variety of other things that we can say. It's amazing, however, how many students, and by students, I mean even the best of students, don't know at its core what slope is. Slope is a measurement of steepness. How steep is a line? And in general, when a line is increasing from left to right, its slope is positive, because when you move in the positive direction horizontally, you also move in the positive direction vertically. And so that ratio is a positive over positive. But when a slope is negative, it means that your line is going downward from left to right, because as you run in the positive direction, you move downward in a negative direction. And so the ratio of rise to run is negative. It's the same idea here. And I'm going to capture this on the next page. A positive correlation indicates an upward trend. And of course, positive has a V in it. And of course, vice versa, a negative correlation indicates a downward trend. Trend does not have an M. Now, I haven't told you how to calculate this number yet. And the good news is, for the most part, we won't. For the most part, all we're going to do is look at the value and interpret it. But that only answers the first question, which was, what direction is this trend for the scatter plot? Are they going upwards or are they going downwards? Positive correlation means up. Negative correlation indicates, not indicates a downward trend. But as far as the second question, which was how linear is a trend, is when you put a scatter plot on a graph, that depends upon the size of the correlation. Before I address that, one comment about correlation. The value of correlation is always between -1 and 1. So it has a very limited range. It can only oscillate between -1 and 1, depending upon your scatter plot. The closer correlation is to -1 or 1, the stronger the linear trend. In other words, if you have a correlation that is large relatively on this scale between -1 and 1, and what I mean by that is, if I were to draw a number line, and put -1 to 1 and 0 in the middle, then the closer the correlation is to 1 or -1, then the stronger the linear trend is, the more close to a line your dots make, and vice versa. The closer correlation is to 0, the weaker the linear trend. So if your correlation on this scale falls like here or somewhere around there, those are weaker. Now, there's always a question What's the boundary between a weak linear trend and a strong linear trend? The answer is there's no set answer to that. Numerically, you would think the boundary would be -1/2 and +1/2 because that's halfway between 0 and both of the ones. But even a correlation of a half isn't very linear. You really kind of have to get, I would say, almost 3/4 of the way to 1 or -1 to start actually looking like a line. And as we look at some examples, you'll see that you can have relatively large correlations like 0.6 that are associated with scatter plots that don't look very linear. All right, so this is one of the measures that we're going to be using to describe the relationship between two quantitative variables, correlation, to answer, is there a positive trend, meaning that the dots go up? And by the way, when the trend is positive, what that usually means is if one of the values increases, you expect the other one to increase as well, meaning that the two values kind of move in the same direction. But if you have a negative correlation, it means that as one value increases, you expect the other one to decrease. And then, of course, the size of the correlation indicates how linear it is. There is a variable for correlation. And just like most variables, there's one for population and one for sample. The variable for population correlation, well, I'll give you that one in a second. The variable for sample correlation is a lowercase r. That's all. Because after all, correlation starts with, well, C. So I'm not quite sure why it's R, maybe because there's 2 R's in correlation. That's a very weak excuse, but the variable for sample correlation is R. The variable for population correlation is the Greek equivalent of the letter R. Does anybody know what the Greek equivalent of the letter R is? It's spelled RHO, it's pronounced rho. If you draw it, and I'm not very good at drawing rho, it kind of looks like a P, except the tail of it is not quite vertical and it doesn't quite close off. I'm not very good at drawing it, but if you'll give me a second, I'm going to open up Microsoft Word because I did learn a trick here and I think I told you about this. If I go into Word and type a Greek letter, excuse me, copy it, and then maybe I can put it back into here. Okay, their row is a little bit more vertical. Ooh, let's get rid of that. I'll show you vertical. Dagnabbit. Okay, that's good enough. All right, so it kind of looks like a lowercase p, which is really bad because later lowercase p is going to represent something else. Oh, wait a minute. We already did sample proportion and population proportion, didn't we? Okay, sorry, my brain was going back and forth between stats 2 and stats 1. And stats 2, we've been doing lots of stuff with proportions. So if you're gonna draw a row to make it look different than P, I would recommend doing what I do. Don't make it quite vertical and don't close it off, because otherwise you're going to see rho, you're going to see P, and you'll rarely see them in the same problem. But I would do your best to make sure that rows and P's don't look alike. All right, so there is a way for calculating the correlation, whether you have a sample data or population data. There's a word I almost used that I haven't defined yet. I don't know if it'll show up in this book this early. The word is bivariate, and it's usually followed by the word data. I assume you know what the prefix bi means, too, as in bicycle or other words that start with bi. But yeah, bivariate data basically means data that occurs in ordered pairs. And that's a good way to look at it, data that occurs in ordered pairs. In other words, things we put on a scatter plot. So anytime we talk about bivariate data, there are 2 variables being measured simultaneously for various cases. But to calculate sample correlation or population correlation, you do have to have a set of bivariate data. And call me crazy, but when you have that bivariate data generically, they are represented as X comma Y, like in algebra. So if you have an ordered pair, you can call its first value X and its second value Y. We won't typically do that, but it is a pretty easy convention to use. I'm going to show you the formula for sample correlation. We will not be doing this, but the theoretical mathematician in me won't let me not show you the formula. The formula for sample correlation is a sum, but that sum has a fraction in front, 1 over n minus 1. It's the same degrees of freedom issue as we saw for the standard deviation. Instead of little n, it's n minus 1. But what's inside the sum, I gotta get rid of this. What's inside the sum is a product of two fractions. For each dot on your graph, you calculate the following. You take its x and you subtract x bar and you divide it by the standard deviation of the x's. Now, if you ever see something for standard deviation subscripted like that, it basically means we have two different sets of values, x's and y's. That's the standard deviation for the x's. And then the other product is the same thing except for the y's. And if you think about it, that's really just the product of the z-scores. Remember, the z-score was how many standard deviations from the mean. So it's the product of, for each ordered pair, it's the z-score for the x times the z-score for the y. And then you add up all those products and then you multiply it times 1 over n minus 1. And then that gives you the sample correlation. We will never be doing this calculation by hand. I'm going to show you in a minute how to use Microsoft to use Microsoft Excel to input bivariate data and ask it for lots of information, scatter plots, correlation, and an equation for something that we're going to call the line of best fit. The one for the population would be almost the same. I'm not going to write the formula, but can you figure out what you would have to change to tweak this for populations? All the x bars would have to become mu's. The little n minus 1 would just become a capital N, no minus 1. What about the s's? They would all become lowercase sigmas. So there is a population version of this, but we are not going to do this. This is just for you to be thankful that you are in a non-calculus based statistics class, because those are a thing. All right, so those are the variables. You do need to know, however, that the variable for population correlation is rho and the variable for sample correlation is r. All right, so what else do we need to know about correlation? I cheated. I wrote down a list of notes that I'm following, you know, like good teachers do. All right, we did that, we did that. What does that say? Oh, properties of correlation. Notes are good if I can read them. All right, so here's some things you need to know. These are called properties of correlation. Some of them we've actually already talked about. The first property of correlation, I think, is it's always between -1. It's always between -1 and 1. It is possible for a correlation to be 1 and to be -1. This rarely ever happens, but just as an FYI, a correlation of 1 or -1, a correlation of 1 or -1 means your points are perfectly linear. In other words, they all lie on a single line. That is statistically impossible. But from a theoretical perspective, that's the only way you can get a correlation of 1 or -1 is if every point is collinear, to borrow a geometry word. Now, it also kind of raises the question, what would it mean for a correlation to be 0? Well, it means you're as nonlinear as possible, but it doesn't quite mean that. I'm not going to come up with an example of a scatter plot whose correlation is 0. I know one example. If you put 4 points on a rectangle, as your scatter plot, its correlation comes out to be 0. All right, number 2. We've already talked about this one. The sign indicates direction. Positive is up, negative is down. And I should say general direction, because when you got a scatter plot, not all the points are moving up or down at the same time, but there's usually a clear trend. Well, it depended upon the correlation. Number 3, we've already said this also. Values close to -1 or 1 are strong trends. Close to 0 are weak trends. So when you're asked to describe a trend, there's usually four possible answers to that. You could say strong positive, weak positive, strong negative, or weak negative. We'll look at some examples of each here in a moment. Number 4, I'm going to take the font size down for a second just so that I can fit all of this on the screen. Number 4, correlation is unitless, meaning that when you calculate it, like for example, let's say that we are comparing hours spent studying and GPA, which are both measured in different units of measurement. One of the variables is measured in hours, the other one is measured in grade points. When you calculate correlation, it has no units. For those of you who, never mind, that's wrong analogy. So whenever you come up with a correlation and learn to spell it, or at least learn to type it, it does not have a unit of measurement. Never, never, never. And then the last thing, correlation is symmetric. Let me explain what that means. When you have ordered pairs, when you have bivariate data, something is going to look like the X and something's going to look like the Y. That choice is almost arbitrary, because if I just switch the ordered pair, my points would all relocate. Without getting into the algebra, if you switch an ordered pair, basically you get its mirror image across a diagonal line, but it doesn't change direction and it doesn't change how close things are to each other. Correlation is symmetric means regardless of which variable is called X and which is called Y, the value of the correlation will stay the same. So it doesn't matter what you call X or Y. And really the better thing to say is it doesn't matter what you call the explanatory variable and the response variable, because normally when you have bivariate data, you're working on this underlying assumption that one of these is causing the other one, or at least that's what we're investigating. So one of them is the explanatory variable and one of them is the response variable. So another way to say number 5 is it doesn't matter what you call explanatory and what you call response, the value of correlation is going to be the same. All right. At this point, I would like to show you how to use Microsoft Excel to draw a scatter plot and calculate correlation for you. It's actually pretty easy. I learned to do it by simply goofing around in Excel. So let me go to Excel because I have it open. Let's see, we're going to do it. Every time I go up there, the number of participants drops. There's Excel. I've already put some data in here. I'll zoom in so that you can see it. I'm assuming the participants that have dropped out are assuming they can watch the recording later. That should be true. I said should be. Monday in the class after this, I recorded it, and for some reason it didn't. So the ones who watched it, good. The ones who are hoping to watch it later, oh well. What we have up here are some data that I stole from an example in the book. The top row represents temperature, outdoor temperature. You'll probably never guess what CPM stands for. You can probably guess the PM part or not. It stands for chirps per minute. Chirps per minute. What kind of critter would we measure chirps per minute? while we're measuring the temperature at the same time. Actually, not birds. Crickets. Yep, crickets. Because there's this hypothesis that the chirps per minute, some of you may have heard this, that if you count the number of times a cricket chirps in a minute, they can estimate the outdoor temperature. Has anybody ever heard that myth, rumor, legend, whatever you call it? I don't know what the formula is, but you can test it by gathering data. And so these are 7 data points that were gathered on 7 different days. These are measured in degree. Well, just looking at these and knowing that they're outdoor temperatures, can you tell if they're degrees Fahrenheit or degrees Celsius? I hope they're not Celsius either, because if they're Celsius, we're all dead. What does water boil at in Celsius? 100. 83 is pretty close to 100. That's like saying it's pretty close to 212 degrees Fahrenheit outside. Yeah, I think we would all be dead. All right, don't worry. Wait a few billion years. It'll happen. That's not a doomsday thing. That's just the fact that stars explode. Sorry, we're living on a time bomb. I know that's very gloomy and depressing, but the good news is that none of us will be around. Okay, but anyway, so we got this data and we want to put it on a scatter plot. The easiest way to do this that I've found is to highlight all the cells, and you can highlight the cells by holding down Shift and then just moving the cursor around. Again, there's a couple of ways to do this, but the easiest way is to go to the Insert tab, and there are some charts over here. If you click on the down arrow on charts, there will be one that looks like a scatter plot, and notice it says scatter. Okay, scatter plot. Now it's kind of already defaulted it. I'm gonna have to zoom back out in order to see it, but it just instantly made me a scatter plot. Move it over just a little bit, move it over just a little bit. Thank you. What happened? There we go. Voila, scatter plot. Now, if I were drawing this by hand, I wouldn't have started this at 0. Let me zoom in on it. I wouldn't have started the horizontal axis on 0 because my lowest number was in the 50s. It's perfectly okay to start at a number besides 0. This one just kind of defaulted that way. But notice that the axes aren't labeled. There's no correlation, whatever that is. So how do we make all that appear? Well, if I click on here, there's a button that says, there's a button that appears that says plus, and it'll allow us to add some things to the chart. If I click on it, oh, look at all these things I can add. But the most important one is the one at the bottom that says trend line. Now, we haven't talked about trend lines yet. That's the next section. But I'm not only going to select it, but I can go over here and choose some more options. If you insert the scatter plot, add a trend line, and for the trend line, click your options. Go to more options. I'm going to type this in the Zoom session here in a second. Choose more options, and then scroll to the very bottom. There's a couple of things that are handy. It may be hard to see from where you are. One of them says display equation on chart. I'm going to go ahead and do that because in the next section, we're going to talk about that equation. But the bottom one says display R squared. Now, it's a capital R and it's squared, but it's something that we can use. I'm going to add it, get rid of that, and move this information to the top so that I can zoom in on it. Well, zoom would be this. All right, so let's say that you click around until you get this stuff on your scatter plot. That R squared is not the value of R. It's the value of R squared. Okay. What can you do to the value of R squared to turn it to the value of R? Square root it. To get rid of a square, you would square root it. Can somebody do me a favor and write down that value of R squared? Because I'm going to ask you what it is in just a second. It's 0.9813. Let's go back here for a second. And let me kind of summarize what I did in Excel to create a scatter plot and to come up with the value of R squared. So we'll call this using Excel to make a scatter plot and calculate correlation. I'm gonna bump the font size up. Hope all of this fits on one screen. Okay, number one, enter your data in 2 rows, and you can actually do it in columns. I usually do it in rows, but it will work either way. Number two, highlight the data. And what I mean by that is where you put the cursor in one corner of the data, hold down shift, and then move around until all the data is highlighted. On the top, click insert, go to, I think it was charts, and select scatter. This will draw a scatter plot. Click on the scatter plot. When the big plus button appears, click it. Insert trend line to the, this is still part of step 5. Insert trend line, and to the right of that, open the menu and click more options. This is easier to do than it is to type out all these words. Insert the trend line, and to the right of that, open the menu and click more options. Scroll down and add the equation and the value of R squared. Now, some of you might be thinking, how are you going to put this on the test? And the answer is I'm not. I would not ask you to get out things that get on the internet during a test for obvious reasons. But on some of the homework questions, they're going to ask you to use technology to get the value of the correlation. There are other ways to do it besides Excel. I just think it's the thing that is most universally accessible to students. I could be wrong, and the easiest one for me to show. All right, so if you do all that, then you can get a value of R squared. We're going to square root it to get the value of R. Now, if you don't want to do all that, not a problem. If you don't want to do all that to get the value of correlation, then I have a backup plan. You're not going to like it. Do this. Average all the X's, average all the Y's, standard deviation of the X's, standard deviation of the Y's. For every dot on your scatter plot, figure out this, multiply it. Once you're done with that, add up all those results, multiply it times 1 over n minus 1, and you'll get the same value. So it's your call. I'll use Excel. All right. Suppose you did that, like in the Excel example. I'm not going to go copy and paste into here. I'm just going to say that we did it. It is in the recording. So if you're watching this recording in the future, well, it's the present to you if you're watching it. Back up the video, go look at the picture in Excel. We got a value for R squared. What was that value? 9813. This is not correlation. This is the square of correlation. But to get the value of R, all we have to do is square root that. 0.9813. And we'll round it to 4 decimal places. Wait, did we have a default number of decimal places to round to? 3? Okay, we'll round it to 3 decimal places. All right, calculator, I need some help. 0.9813 square rooted to 3 decimal places, 0.991. And that's the value of the correlation for that cricket chirping temperature scatter plot. All right, does anybody have any questions about where the R came from? Then I have a question for you. Actually, I have 2 questions. Question number 1, based on that value of correlation, how would you describe this trend? Think about that number on that spectrum between -1 and 1. There's two words I'm looking for. First word, weak or strong? Strong. The closer you are to 1 or -1, the stronger you are. That's pretty darn close to 1. This is a strong, and the other one is whether it's positive or negative. Clearly, this one is positive, but not for the reason that you think. It's a strong positive trend. If you're thinking I said positive because when I square rooted that number, it came out positive. Yeah, anytime you square root a number, it comes out positive. There is a warning when you do this method to calculate R. I'm going to put an asterisk here, and I'm going to define it right here. I'll type the definition because, well, my writing leaves a lot to be desired. And I'll take it down a notch. If you use this technique to calculate R, where you go into Excel or any technology and get the value of R squared, and then you square root it, it will always come out positive. But from the scatter plot perspective, when would you expect the value of R to be negative? When it's a downward trend. So here's the asterisk. If that was supposed to be red, just because I wanted it red, if the scatter plot shows a downward trend, make sure you put a negative sign on this value. Because again, from a numerical perspective, when you square root a number, it will always come out positive. It has to do with defining square root as a function, but we'll spare the algebra discussion. However, if you need the answer to be negative, then you have to manually insert the negative on the value, and the evidence that it should be negative is that your scatter plot displays a downward trend. All right, so any questions about describing the trend or what I'm saying in the red there? Okay. Well, if we're going to come up with very strong, slightly strong, anemic or whatever, then we would really have to set up some boundaries from a numerical perspective that say, once we cross this boundary, you're very strong. I don't even know the boundary between strong and weak, to be honest with you. I mean, we could all say, fiddle around and say, okay, I think it's this one, but we probably won't use very at all. We'll just say that's all I'm going to hold you accountable for. Is it strong or weak? Is it positive or negative? Now, as far as discerning between strong and weak, when I ask you to make that determination, I will make it fairly clear. This one, really strong. 0.2, weak. 0.55, no, I wouldn't ask you to describe something as strong or weak unless it were really on the extremities or really close to the middle. Okay. Otherwise, if you're in that gray zone, it's not clear when you stop saying weak and when you start saying strong. Okay. All right. We just got one more thing to do in this section, and it's some cautions. You've heard one of these cautions already. These are called, appropriately enough, cautions about correlation. Number one, you've heard this before. And I'm going to put the word strong in the front of this. Strong correlation does not imply causation. I don't care if it's perfectly linear. Well, if it's perfectly linear, there might be an exception there. But a strong correlation does not imply causation. So even on the last one that we saw, where the line going through the dots, and I'm going to go back to Excel just to show you real quick. The line going through the dots from the crickets, chirps per minute, and the temperature of the day. I mean, that is very linear. It's hard to get that linear naturally, but even in a strong correlation like that, it's not enough evidence to say, well, the temperature is causing the number of chirps. It's suggesting it, but we would need further evidence. I'm not sure if we could conduct a double-blind study with crickets. They probably don't know that we're counting their chirps anyway. But yeah, even though strong correlation is not enough evidence to say, therefore, causation. So that's warning number one. But we kind of already, said that. All right, number two. Number two is kind of the opposite. A weak, well, no, I don't want to put that in parentheses. A weak correlation, what I'll put in parentheses is near zero, does not necessarily imply the lack of a trend. It simply implies the lack of a linear trend. I'm going to highlight the word linear because that's the key word there. There can be a clear trend. It might not just be a line. Does anybody know what exponential growth looks like on a graph? It's a graph that starts out growing slowly and then it skyrockets. It's how interest grows when you invest money. The longer you leave it, the faster it grows towards the end, which is why the time to start retiring was the moment you got your first paycheck. But that's a story for business math, not this class. But there may be a trend. It just might not be linear. Correlation measures how strong a linear trend is. And the third thing, well, I'm going to kind of get you to show me the third thing. And to do that, I need to go back to the textbook for a second. And let me find what I'm looking for. I know exactly what I'm looking for. It'll jump out here in a moment. Curse you, McDonald's, and that stupid jingle. You know, the one that goes ba-da-ba-ba-ba. I can't get it out of my head. And now you can't either. All right. I want you to look at, forget this little spillover on the left, which is kind of funny because it's alcohol. I want you to take a look at that scatter plot and look at all them dots. They're real close to each other. They kind of form a pretty horizontal trend. But are you looking at all the dots? Oh, by the way, this is measuring calories consumed in a day. Yes, calories consumed in a day on the bottom and number of alcoholic beverages per week. There's a reason all the dots are living in the lower left-hand corner, because somebody in this bivariate data set is either incorrect or very, very, very alcoholic. You see them? Where are they? Look in the upper right-hand corner. Yeah, do you see that dot up there? Probably not. This person, when they answered the question, how many calories do you take in per day? Was it daily or weekly? I know I just said that, daily. Okay, it's not impossible to take in over 6,400 calories in a day. I'm not sure if it's advisable, but forget that. This is how many alcoholic beverages they say they're drinking in a week. I believe it's a week. Yes, drinks per week. I don't drink. Well, I rarely drink, but I'm pretty sure having over 200 alcoholic beverages in a week is not the norm. I mean, y'all are college students. You probably drink more than I do. If you drink anything, you drink more than I do. But over 200 per week, that's like over 30 a day. Well, around 30 a day. Well, under 30 now. No. So why did this person say 200? Well, either they're lying or they misunderstood the question. But anyway, when you have an outlier, and that would clearly be an outlier, you have to zoom out really far to see all the dots just to pick up that outlier. And it might look like that these are tighter than they really are. If we remove the outlier, it looks a little bit more like that. And although there are some steady dots down here, namely people that don't drink, if you look at the big picture, there's not a clear trend. When there's an outlier, it forces you to zoom out to see it, which makes all the other dots look closer than they are. So the third caution about correlation is obviously about outliers. Outliers greatly affect the value of the correlation and hence distort whether or not there really is a trend. To kind of show you what I mean, I'm not going to manually calculate the correlations for the two scatter plots that I just showed you. I am going to go back to them in just a moment. I know people are writing there. Before I go back, which of the scatter plots do you think had the smaller correlation value? The one with the outlier, or the one with the outlier, or the one without the outlier? Which one do you think had a smaller correlation? Let's go back to the pictures and see. If you're writing that down, don't worry. It'll be back up here in a moment. Let's take this down a couple of notches so we can see both of them. Remember, correlation attempts to measure two things: direction and how linear it is. So of these two, when I'm asking you which one do you think has the greater correlation, which one do the dots look like they're closer than they are? The first one. The value of the correlation on the left picture is 0.72. Not super strong, but fairly strong. The value of the correlation of the picture on the right is 0.15. Just that one outlier threw the correlation off from 0.15 all the way up to 0.72. So yeah, outliers. By the way, in your book, these pictures are on page 125, the ones I'm showing you up here of the alcohol versus calories. But yeah, correlation is greatly affected by outliers. Usually it inflates the value because you have to zoom out really far, which makes the rest of the dots look closer than they actually are. All right, but those are the cautions about correlation. And with that, looking at my checklist, we have finished. Let me turn my phone down. We have finished this section. All right. So it's time for your homework assignment. I will put this in Canvas in the place where I put all the homework assignments, but I want to go ahead and put it here as well. The homework assignment for 2.5 is on this piece of paper. It is on page 126. I would like for you to try the following. It starts with 186 through 193. And I know that sounds like a lot, but they're matching questions. So you don't figure anything out, you just match stuff. Then I'd like for you to try 200, 202, 204. Then 212, 218, 226, one more, and 230. The last batch will take more time than the 186 through 193, because again, those are just matching. They're matching in terms of correlations to pre-existing graphs. In fact, why don't we just go ahead and take a look at a few of the beginning ones just to show you what I mean. I don't know if these homework problems are exactly the same as the ones I assigned you. And of course, there happens to be a page break between the values and the graphs we're going to match them to. I know they're kind of hard to see, but this first batch of 4, and I'll write them on the board up here. Sorry for those of you on Zoom. -1, 0, 0.8, and 1. And then they're basically asking you to match those correlations with these 4 graphs. So let's just talk about it for a second. Which of these scatter plots, A, B, C, or D, do you think has a correlation of -1? B. 1 means perfectly linear. Negative means downward trend. So this one would be -1. Which one do you think is 0? C. Look at that scattered, completely nonlinear mess. Correlation of 0. Which one do you think is 0.8? D. Why is it not A? A is 1, because A is perfectly linear in a positive direction. And if you look at D, and I want to zoom in on it for a second, because this makes my point about it's kind of hard to decide when do you stop saying strong and say weak, or just say positive without either adjective. This graph has a positive correlation, and based on our choices, it has to be positive 0.8. Those aren't that linear. I mean, they're kind of all going upwards at the same time, but to call this a line would be almost laughable. So even 0.8 doesn't look that strong, but if I just asked you to call it strong or weak, I think you would have to call it strong. All right, as opposed to things like this. Now, I'm not going to do these because this is the next batch that you have to do. You know what? Some of these you just got like, well, like this one. Forget strong or weak. Would you say positive or negative? I'd say from left to right, they're generally moving downwards, because on the left, I got this one way up here, this one down here. So if you force me to say positive or negative, I'd say negative and weak as well. What about this one? Negative, a little stronger than that one, which means that it would be a little bit closer to -1 than this one. And as far as these two, okay, this one's pretty clear. It's positive trend and probably a fairly decent sized number. This looks like a scattered mess. I don't even know if I could decide if that was a upward or downward trend. But you know, whichever our answer choice is, it's going to be fairly close to zero, probably the one that's closest to zero. So that's what the first few questions on your homework are. Here's 4 correlations. Here's 4 scatter plots. Match them up. And yes, on your test, I will ask you that type of question. Here's 4 scatter plots. Here's 4 correlations. Match them up. All right. Any other questions about the about correlation, upward trend, downward trend? Cautions, homework. This is the last homework assignment that will be part of the quiz that I write. I always say that I'm going to write the quizzes on Friday, and I usually get them started, but sometimes I don't finish them. So let's just say that the quiz will be available before I see you again. I shoot for Friday, but I don't want to wait until Monday to get it done. But, you know, if it doesn't happen Friday, it will happen. And if you just can't wait to take it, you pester me with some text messages until it's done. Say, hey, where's quiz? I'm ready. Okay, I'm finishing it. Take some time to write those. All right, we're going to go ahead and begin the next section. I don't think we're going to finish it. I do have a list of bullet points that I want to say. I don't have a homework assignment chosen. In the unlikely event that we finish it, I'll be kind of surprised. But, you know, stranger things have happened. This is the last section in chapter 2, and it is called, surprise, surprise, 2 quantitative variables. And if you think about it, the development in this chapter was 1 categorical variable, 1 quantitative variable, and now we're doing 2 quantitative variables. We can do 2 categorical variables, but then it gets into stats too. But it's called 2 quantitative variables, linear regression. And we've kind of gotten a sneak peek at it. Because when we did that, that scatter plot in Excel, we kind of also did the regression. I'm going to go back to the scatter plot for a second. Excel. The scatter plot are the dots. The R squared is our ticket to correlation. We just have to square root it, stick a negative if the line's going downward. But what in this do you think is the quote unquote linear regression? Hint, it's not the dots and it's not the R squared. There's not much else up there. The X's and the Y's, sort of. There's actually 2 ways to view what's called a linear regression up there. Number 1 is the equation, and number 2 is that line going right through all those dots. But both of those are examples of what's called a linear regression. It actually has 3 names that I use interchangeably. First one is called linear regression. Second one is called line of best fit. I think that one makes more sense. And the third one is called the least squares line. We're going to talk about all of those different names and why it gets to be called 3 different things, but they're all pretty much the same thing. So all a linear regression is, a linear regression is just an equation associated, a linear equation associated with a scatter plot. And more specifically, I should say associated with bivariate data. but we can just think of it as a scatter plot. The equation attempts to locate the unique line, and it is unique. You don't have to call it the unique line all the time, but I just want to mention that it is unique. The equation attempts to locate the unique line that is, and for lack of a better word, closest to all of the points in the scatter plot. From a technical perspective, we would have to define what do you mean by closest by somehow coming up with a way for measuring how far a point is from a line, and then coming up with the line that is quote unquote closest. Now, have any of you actually done a linear regression before, like in a TI calculator where you put data in and push buttons and suddenly it draws a line? Some of you might have done that like in a high school class or something like that. It's pretty much the same thing. But I'm not going to require that you go out and buy a calculator that does that. So when we had that, that scatter plot in Excel, the line and its equation, either one could be called the linear regression. Before we go any further, does anybody know, not to sound flippant or anything, but does anybody know what linear means in this context? It's not what you think. Algebraically, the word linear has a very clear definition. Most people say line, and that's the reason the word linear was chosen, but that's not the definition of linear in an algebra perspective. In algebra, the word linear actually means highest power is 1. You all know that in algebra, letters normally have powers: x, x squared, x cubed, x to the 19th. Okay, that's pushing the envelope. But the word linear in algebra means that whatever you're dealing with, variables, the highest power is 1. If the highest power is 2, it's called quadratic, a la the quadratic formula, and there are other adjectives. But linear means the highest power is 1. And the adjective that was chosen, linear, it was chosen because when you graph that type of equation, it makes a line. So, but algebraically speaking, linear means that the highest power is 1. So these equations are going to have variables, but just with powers of 1. All right, I want to just briefly sketch that scatter plot. This is going to be a very rough rendition of it. We had some dots. We'll use some, what shape do I want to make my dots? Stars, hearts, checks, X's, hearts, okay. Oh, how sweet. All right, so on that previous one, when we had this line and it looked something like that, and it gave us that equation of the line, and I don't remember what the equation of the line was, but I am going to go back to Excel just for a second. Zoom folks, you're not going to see me switch back to Excel, and I'm going to do the lazy thing. Instead of writing it down, I'm going to take a picture of it. Picture lasts longer unless your phone dies. All right, let's go back to Zoom. That would be this one right here. And in that Excel scatter plot, we had an equation, and the equation was, this is why I took the picture, y equals 4.2544 x. I'm going to have to move that. I'm not leaving myself enough room to write the rest of it. So give me 1 second to relocate it. And then there was a minus 157.82. And again, this comes directly from that Excel example with the chirps per minute for the crickets and the temperature. In fact, I forgot which one was which. I'm going to look at Excel again real quick. The X was the temperature and the Y was the chirps per minute. So X is equal to temperature, and Y was equal to chirps per minute, CPM, if you will. Yeah, earlier I asked if any of you know anything about slope, and I heard y equals mx plus b. I heard rise over run somewhere, and both of those were good and correct answers. But does anybody remember, how many of you remember y equals mx plus b? Not what it means, just seeing those letters. Okay, several of you. That's one of them. Does anybody remember what either the m or the b was in y equals mx plus b? No, you just remember the letters y equals mx plus b. All right, what if I told you one of these numbers was a slope? It's well, which one's the m? The 4 point something or the 157 something? 4 point something. Yeah. When you have this equation, the number in front of the x is your slope. In y equals mx plus b, that's the m. But what about this number at the end? Does anybody remember what it represents? The y-intercept. Meaning if we stretch this line out until it crossed the vertical axis, that's where it would hit. Now this one isn't drawn to scale, but if I were to continue this line, that's where it would cross at negative 157.82. So are we going to be seeing these equations in slope-intercept form? Well, yes, but no. What the heck do I mean by that? Here's what I mean. For a linear regression, the equation will always be written in the form y equals a plus bx. Don't worry about the a and the b. Those are just playing the roles of numbers that we don't know. The important thing about the structure of this equation is that the term contained in the x is written second instead of first. That seems like an arbitrary change, but there is a reason in statistics why this equation of that line is written with the intercept first and then the term containing the slope second. I'm not going to get into the stats 2 details, but the reason is we're dealing with 2 variables right now, one explanatory, one response. When this happens, what do we expect that to happen? In stats 2, we push the envelope further and say, well, this guy might be responding to explanatory variable number 1, number 2, number 3, number 4, number 5. And so in stats 2, you get a more multi-dimensional linear equation that starts with whatever your intercept is, and then is followed by a bunch of different variables with different slopes. So this is just a small precursor to that happening in stats 2, but you won't see that unless you take me for stats 2 in the spring. Yes, I'll be teaching it. All right, shameless plug. All right, so anyway, our linear regression equations will be written in the form y equals ax plus b. And the other thing I don't like about this generic form, the fact that the x is second is almost arbitrary. What I don't like is that they call the slope b. Because in every y equals mx plus b that you've ever heard, the m was the slope and the b was the y-intercept. But in this form, the a is your intercept, and the number sitting in front of the x, which is currently called b, is your slope. The fact that it's called b is inconvenient, but at the same time completely irrelevant, because when you see your equations, they'll just be written in what looks like backwards form. So for the one that we had, we would actually write the intercept first, and I don't remember what it was. Maybe you can tell me. What was the intercept? Negative 157.82. And I remember the slope was 4 point something. 2544. So it's just a big fancy way of saying the equations are going to look a little bit backwards from what you've seen in college algebra. Instead of y equals something x plus something, it's y equals something plus something x. All right. There are formulas that can take the bivariate data and calculate both the slope and the y-intercept. I'm going to spare you even showing you the formulas, but they're kind of as obnoxious as the formula that I showed you earlier. All right. So, so let's say that you have this bivariate data and you turn it into a scatter plot and you turn it into this line that kind of represents the best line that's closest to the data, whatever that means. What can we do with this line? Well, here's one of the nice things about data, and this is really what the world attempts to do with data. People gather data to try to predict the future. That's why data is gathered. What's happened in the past, and can we use it to kind of predict what's going to happen in the future? And the way that plays out here is a linear regression. And again, that's just a fancy name for that equation. Can be used to attempt to predict future values. I'll show you an example. This time I'm going to type the equation. I forgot I took a picture of it. I'm going to type the equation. The regression, y equals negative 157.82 plus 4.2544x was calculated using data where x equals temperature, and y equals chirps per minute. Or did I do that backwards? 1 second, I need to look at my picture. Yeah, these are temperatures. We had a number that high? Data sets up here. We did. Okay, we did have a high chirps per minute count. All right, that makes, well, we certainly didn't have a temperature that high. Hey, it's 195 outside. We're dead. All right, so yes, we had x equals temperature and y equals chirps per minute. So that is what we had. Okay. Using this, predict the chirps per minute when the temperature is, oh, I don't know, we'll say a balmy 82 degrees. This is an algebra problem now. I'll just throw it out there. Does anybody know how I'm going to use the equation to attempt to answer this question? Yes, sir. And what is the x value? We're going to plug in x equals 82 and then figure out what y equals. Because we're being asked to predict chirps per minute, we're being asked to find out what y equals because that's what it says right here, y equals chirps per minute. So this is just a plug and play, if you will. And I realize I misspelled temperature. Not sure if I'm going to go back and fix it. This being a temperature is a value of x. So we just have to substitute x into the equation. Negative 157.82 plus 4.2544 times 82. And that equals something. That's what calculators are for. Negative 157.82 plus 4.2544 times 82. I got to the nearest whole number, 191. Did anybody happen to put it in a calculator and get kind of the same answer? Okay, just wanted to make sure. All right, so we can kind of predict, hey, when it's 82, I predicted these crickets are going to chirp 191 times per minute. Now, is it guaranteed that's going to happen? Of course not, because that line did not perfectly hit all those dots, but it was close. So if it's a good model, then we would expect something around 191 chirps per minute. But it also works backwards. What would I mean by working backwards in this setting? In this example, we use the temperature to predict chirps per minute. So what would it mean? How would you work that backwards? Use the chirps per minute to find temperature. So let's say that you're out at Tyler State Park or something, and for some reason you have a picture of this on your phone, and you're just sitting there enjoying the breeze, waiting for the sunset, and you just randomly start counting cricket chirps. And then let's say that, for example, if you count 162 chirps in 1 minute. Predict the temperature. Or really, I don't know if predicting would be the best verb here. Maybe estimate the temperature, because you really can't predict what's going on right now. Let me predict the present. Wow, you're an awesome prognosticator. You can tell me what's going on at the moment. But yeah, it works the other way around. But in this case, the 162, is that a value for X or a value for Y? It's for Y. We said Y equals chirps per minute. So we're going to let Y equal 162. And if we do, we get 162 equals negative 157.82 plus 4.2544x. And now it's a little bit more algebra and not as much arithmetic. The previous example was arithmetic because we just did number math and got a number answer. This is algebra because we have to undo the math in order to solve for the x. I know it's not an algebra class, but can anybody tell me what algebra moves I would have to do to start getting the x by itself? Add this number to make it disappear. Let's do that, and then I'll give you a chance to finish it. So plus 157.82. As soon as I add 162 plus 157.82, 319.82 is the sum. The negative 157.82 cancels on the other side. That leaves us 4.2544x. And as you said, to undo the multiplication, you would divide both sides. You divide both sides by the number that you don't want on the x. So 4.2544. And so we get x is approximately, we'll round it to the nearest whole number, divide that by 4.2544, and we get about 75 degrees. Because that's clearly what you would think if you were out at Tyler State Park. You know I'm being facetious, I hope. All right, so you can use a regression to try to make predictions in both directions. All right, so any questions about using that equation to try to make predictions? Okay. All right, so to wrap up the discussion today, this will take about 3 or 4 minutes. Oh, you know what? We can't do that yet. We'll do the next thing and we'll see what happens. Next thing won't take very long. The next thing is a concept. You remember earlier when I said, how are you going to see how close a line is to a point on a scatter plot? How are we going to measure the distance? Well, we measure the distance from a point to the line using something called a residuals. So I'm going to define what a residual is. For an ordered pair in a bivariate data set, for an ordered pair in a bivariate data set, and let's call the ordered pair x comma y. The residual is the observed y value. So in other words, in that pair, it's the difference, it's the observed y value in that pair minus the predicted y value from the equation using the observed x value. Now, I know that's a lot of words, but think of it this way. When we have an ordered pair, we observed an x and we observed a y, and we put them together and said, look, an ordered pair. But when we come up with this equation, we can use it to make a prediction. So we're really just figuring out the difference between what y value did we see versus what y value does the line predict. So using the previous example, suppose we observed, what was the number we put in for the chirps per minute in the first example? I'm sorry, that was the wrong question. I think that was the right answer. When the temperature was 82, we predicted 191 chirps per minute. That's what I meant to ask. So suppose we observed a temperature of 82 and chirps per minute was 185. I'm going to put CPM there to remind you that's chirps per minute. The 82 is the observed X value, and the 185 is the observed Y value. So let's say that we observed that. Oh, it's 82 degrees outside, and that cricket chirped 185 times in 1 minute. Using the equation, because we've already done this, when X was 82, we got Y equals, I don't remember what we got. I can go back. When X was 82, we got Y equals 191 back here. So the residual for this ordered pair is the Y value that we observed 185 minus the Y value that the equation predicted. 185 minus 191 is -6. There's a visual component to this, but numerically speaking, the residual, and maybe I should have started with this. I probably should have. The residual for an ordered pair, I'm going to scoot this up just a little. The residual for an ordered pair is the observed Y value minus the predicted Y value. I'm going to take the dash out of Y value. It looks like a subtraction sign. The observed Y value minus the predicted Y value. The observed Y value is the Y value you observed along with its X value. The predicted Y value is the value that was predicted based on that observed X value. It's 5:30, so we're done. I got to stop looking at that clock. Will that clock come off the wall? Is anybody tall and willing to try to take it off the wall? Okay, well, I'll go over there in a second. All right, so we're done. Keep an eye on Canvas for the quiz over 2, 3, 2, 4, and 2, 5. And Zoom folks, if you have any questions, drop them in the chat. I'm going to step away for a second and answer them if I see them. All right, see if we got any chitty chat. We do not. Who's left? Hey, Karina, thanks for being on. I'm about to end the Zoom session. Oh, she's gone. All right, so we're going to stop the recording.